Today, I'd like to talk to you about an incredible monument that is in North America, in Ohio. It's been fairly much destroyed over the past 100 years by the building of the town and the golf course and all kinds of things. But a lot of it is still remaining, and it enables us to see incredibly advanced geometry and astronomy, which took place before history started in the United States, in North America. So let's go in and see what this is about. Maybe some of you know about the Newark Octagon. It's Newark in Ohio. Maybe some of you have never heard of it, but let's see what it's about. So it's very interesting to do my talk at this particular time. I first wrote a paper about this site in 2019, which is on academia. But I'm talking about it now because there are two reasons for this. One is that the site has recently been made open to the public, or will shortly be made open to the public. Up until now, it's been a golf course, it's been closed to the public, and there's been a struggle, a legal battle going on for 18 years, over 18 years, to try and open it to the public. And now the decisions have been finally passed in all the different levels of court. And so from 2025, it'll be open to the public. And that's very important because 2025 is a very important date for the astronomical observations that can take place there. So we'll go into this. First of all, let's have a look at this monument. So it's composed of a massive circle. These are banks which were built with earth, trenches and banks, and about 1.7 meters high, so a little under 6 feet high, and quite wide at the base, a few meters wide at the base. And it's the massive scale of the thing that's incredible, because the major monument I'm going to be talking to you about today is nearly 1 kilometer long. Okay, so very big scale of things. And here we've got some photos taken, aerial photos taken in the 1930s, which I took off Wikipedia. They belonged to somebody called Carp Trash. And you can see here the banks. There are two banks going up here, and then a form going off here and up here. So this is the form of an octagon. And this photo is very, very interesting because you can see here the circle. This is a massive circle here, which goes to this little opening. And then from there are these banks which form an octagon. Along this bank here, there are trees along this bank here. And then you can see the other bank going along here. Outside of the bank is another small circle. And then there are two other banks in the foreground, which we can't see, but this photo gives us a pretty good view of the whole thing, which is very difficult to see when you're on the ground. When you're actually in the monument, it's very difficult to see the thing as a whole. It just looks like banks on a golf course, basically. So let's go into this and see. You can get photos of this now on Google Earth. So we're going to zoom in here. So here you can see, here's the golf course. And you can see here a circle here. It's a virtually perfect circle. And then there's the little pathway here. And then there's the octagon shape. So let's highlight those. So that's the octagon. and that's the observation circle. And there is an axis. There's an observatory mound here. So we'll go in and look at this. Right at the end of the circle, here at the bottom of the circle, there is a big mound which is higher than the rest of the banks and which enables observation to take place along the major axis, along the circle, through this sort of pathway and through the opening between these two banks here. Now you can see it's written mound A, B, C, D, E, F, G, H, because inside of the octagon, just inside each opening, there is a mound which is positioned in a special way, and I'll be going into that in the second part of this talk. Okay, so that's the general shape of the monument, and if we go and see some details, so let's go in and see the observatory mound. So somebody has done all the photos here on Google. So now I'll take the different lines off so we don't see them. There we go. So here you can see in the distance, this is the bank of the circle you can see in the distance, and we can see it round this way. Here we can see the bank going round in this direction all the way round, so you get some kind of idea of the scale of it. Okay, and here you have the observation bank here, which as you can see is higher. It's slightly outside, just behind the back of the circle. There's an opening here, right? And just behind the back of the circle, you have this higher bank, which is called the observation mound. The man who was doing the photos was with this lady here, who's going to be on all the different photos we'll be looking at. So these banks are called the Hopewell. They're part of the Hopewell civilization or Hopewell tradition. Hopewell is the name of the place that they were first discovered. And they date from, at the earliest, 500 BC to the latest, 500 AD. So there's a kind of 1,000-year opening there where the Hopewell people were moving around the Ohio River, which is a kind of snake-shaped, it's serpent-shaped river. And they were building things all over the place. And again, in the second part of the talk, we'll be looking at some other places. So there we are. Now, let's go and have another look at another part here. We can go in, for example, see this junction part here between the circle and the central axis here. So here you can see this sort of central pathway going down here, and that is directly linked to the circle here, which then goes off right round there on a long distance. See, it's very big, you can hardly see the other side, and comes round here. And then we'll just go up the other end to the point where it meets the octagon. Let's have a look. So here we can see the octagon shape, but if we come in here from this point, for example, we get quite a good view of the banks. There you can see how straight, how perfectly straight this bank is, and then the other bank going off at an angle like this. And this is the mound, which is just inside the entrance. Okay. So that's the overall view of the monument. Now, this monument was first seen in 1837, and a plan of it was made up. And I've superposed the plan over the existing thing. And you can see that, in fact, there are a lot of other things. There's a big circle here, which I won't talk about today, but I'll talk about next time. It's not a perfect circle. This one's slightly off. And there was a square here. Again, a square, which has totally disappeared. There's just a little bit of a bank somewhere there. And there were different other things, but of course this is all now in the middle of Newark, okay? And there was also a massive pond here, and now there are houses in all this area. I don't know if people have rising damp, but so it was a landscaping, artificial landscaping on a very large scale, okay? Now, as far as the octagon and the observation circle are concerned, there was a study done on this in 1982 by two researchers called Ray Hively and Robert Horn from Earlham College in Richmond. 1982 is when they published it. Their study took place in 1980. This was right at the beginning of personal computers. In 1980, you couldn't on your own do all kinds of things that you can do now, especially incredibly detailed calculations of astronomical phenomena. And they did this survey, and they came to the conclusion as follows. They say in their introduction, "Our analysis shows that the earthworks conform to a simple but precise geometrical construction based on a single unit of length." They say simple but precise. It's not all that simple, as we'll discover in the second part. But it's based on a single unit of length, which is very interesting. And this same unit of length can be found in other sites many miles away from the Newark Octagon. The same unit of measurement is used. They say also, "Our work has revealed substantial evidence that the earthworks may have been laid out, at least in part, as a lunar observatory." And that's the part that has been maintained. People have accepted this idea that it was a lunar observatory, which is why people have been wanting to go there to watch the moonrise, and why there's been some conflict over the place. I'd also like to point out that they do say in their report that since no radiocarbon dates exist for Newark, the date suggested has been reached by comparing ceramics and, for example, the style of platform mounds in the Newark Octagon with similar sites where radiocarbon dates have been secured. So the dating of the Newark Octagon is simply by comparison with other places, comparing ceramics, for example. But you never really know if the ceramics were left there by people who built the site or people who were just staying there. So let's look at some more of their conclusions. On the top left here, you have the diagram that they've made with the lettering, marking all the different major points. And they of course, mark out the major axis, and they give a measurement for this major axis. Now, they compare here with a man called Middleton, who did surveys, very precise surveys apparently, in 1887, 1888, before some restoration work was done on the site, because one of the dangers here, because there has been restoration work done on some of it, is to say, has it been modified? Can we really consider this site to be exactly how it was when it was built? And although they are a bit doubtful about that at the beginning of their report, they finally come to the conclusion that there are very few alterations, maybe a little alteration, the height of the mounds, but certainly no alteration in the orientation of the mounds, because they're getting the same results virtually as Middleton got in 1887. It's just some of the mounds might have been made a little bit longer, and one of the mounds in particular may have been a little bit shorter. So it's very small modifications to the initial building. And so they give the general angle here as 51 degrees and 50 minutes, which if translated into decimal is 51 degrees, 51.83 degrees. Now that is the angle that I get when I take the angle on Google Earth. We can go and check up on that. Good idea. So we're going to zoom in here down to the observatory mound. Here you can see it, right? So we're in the middle of it here. And if we put a point on here, okay, and we go up along this line through the center. So this red line goes through the center of the observation center, through the center of the middle pathway, through the center of the octagon, which I haven't put on here, have I? No? Well, we'll put on the two diagonals and you can see where the center is. Okay. The diagonal. There you go. So we get the center here of the octagon. And so we can see here that we have 51.83 degrees. You can see there are two lines, okay? This lower line goes to a high point in the distance. It's exactly 51.83 degrees. And it goes to a far off foresight in the distance, right, on the hilltop here, which is where the moon would have risen. That's where it would have come out of the horizon at that particular point. And I'll be coming back to that in a second. Okay. So 51.83 degrees seems to be a very good and precise value. And they have a measurement between K and N here of 322.5 meters, which is 1,058 feet. And that's the same measurement that Middleton got in 1887. Now, they give a lot of different other angles here, and they go into the idea that certain sides of there are different viewpoints you can take, like the sides of the octagon and viewing between different parts. And again, I won't be going into that today. I'll do it when I talk about the geometry next time. So I'm going to be talking about this major axis, okay, which we see is 51.83 degrees. And here's the moon. You can see the moon, the full moon here. And of course, when we talk about watching a moon rise, we often think about watching the full moon rising up out the horizon. But what they're going to show here is they're not going to talk about the full moon or whether it's the half moon. They're talking about the date of AD 250. So they take a date of AD 250 and they measure the azimuth. Now, although they measured it before, as we saw, at 51.83, they say here that it's 52.0, which is something I haven't quite understood, why there's a difference between what they say in their report and what they put in this table. There's a horizon elevation. So where the moon rises is slightly higher, about half a degree, they say, 0.51 degrees. And so that will change slightly the angle. I'll show you that in a minute. It changes slightly the angle of the moonrise because the moonrise will be delayed by the hills in the distance. And they give here the lunar azimuth, the orientation of where the moon will rise, as 51.8 degrees, but they don't say which part of the moon they're talking about. Are they talking about just the first tip of the moon, or the center of the moon on the horizon, or the moon sitting on the horizon? Because the moon moves on an angular basis, the angle changes according to which part of the moonrise you're looking at. So I'll come to that in a second. But they don't mention it here, which is a bit of a mistake, because one can suppose they're talking about the center of the moon, but they don't actually say so. So anyway, the lunar azimuth they give here, 51.8 degrees, is in concordance with the angle we saw of the major axis, but slightly less than the angle they say they measured, and they give a 0.2 degree error here. Okay? So that's the angle they calculated for 250 AD. Now, that means then that this angle corresponds to the maximum north moonrise in autumn. The maximum north moonrise can also be called a lunar standstill because it's a moment where each time that the moon comes to this point, it kind of stays there for a bit. It's the equivalent of the solstices for the sun. It's the moon standstill, okay? And this moon standstill moves over a period of 18.6 years, and it comes to a maximum position every 18.6 years. And as I said at the beginning, that's happening right now in October, November, December 2024, and up to about April in 2025. Probably the best time to go and watch this would be at the full moon just before winter solstice, around the 15th of December, I believe. Although you should check up on that if you want to go. Now, what is the maximum lunar standstill? So it's a cosmic event that happens every 18.6 years, and it's happening right now, as I've just said. Here I've done a table showing how at Newark these angles are moved. So what we can see is there are 8 different lunar directions on the horizon which limit the moon's displacement as it rises and sets over an 18.61 period. So we have these maximum positions, maximum moonrise here, maximum moonset here, and that's the maximum moonrise to the north. But then when the moon is at its maximum moonrise to the north, then 13 or 14 days later, it then has its maximum moonrise towards the south because the moon goes up and down the horizon in 27 1/3 days. So it's a movement that you have to sort of watch, really. You have to observe it to be able to understand it. And so you also get the extreme positions of the moon sets, and these go further north than the summer solstice sunrise and sunset, and further south than the winter solstice sunrise and sunset. So the moon goes outside of the sun's limits over the year. And then you have the minimum moon sets here, which are when the moon is actually inside and doesn't go as far. So the sort of amplitude of its movement is much smaller on the horizon. And here these moon rises correspond to days in the calendar. The sun will also rise along those orientations on specific days. And in previous work, I've gone into a lot about this in Europe and how certain feast days, although they're fixed days in the calendar, are linked to the moon. Okay. Now, Wikipedia says about the term lunar standstill that it was apparently first used by engineer Alexander Thom engineer and professor from Oxford University, in his 1971 book, Megalithic Lunar Observatories. Now, Professor Tom was a total pioneer on this question, which means that even the term lunar standstill, which is a sort of a cosmic event, you know, it's a planetary, or it's linked to cosmic movement. He actually coined this term because nobody had been talking about this before he got interested in it. And he suggested that the megalithic builders in England, Britain, Ireland, and France, Karnak, had been building their monuments with respect to these extreme positions of the moon. If you know these extreme positions of the moon, then it's easy after that to calculate eclipses. Okay? So he wrote this book, Megalithic Lunar Observatories, which was a really new set of ideas, and which a lot of people had trouble accepting and still do. But here at Newark Octagon, the idea that it's a lunar observatory linked to the maximum moon seems to be generally accepted, which is a very good thing. So the lunar standstill phenomenon was probably known from megalithic times. This is Wikipedia saying this. In high latitudes, so in other words, if you go up near the Arctic Circle, there was a period within the 18.6-year cycle when the moon became circumpolar. So we have the midnight sun, and you would have had the midday full moon. The moon would have not set. It would have gone up and down in the sky on a circle like that, which, of course, that wouldn't happen all the time because of this variation in the moon's declination, as it's called. So at the same latitude, sometimes the moon would be visible at midday as a full moon in the sky, and at other periods it wouldn't be. So that obviously must have attracted a lot of attention. So that's from Wikipedia, the site on lunar standstills. I give here in this diagram the angles, so 51.83 degrees for the moonrise here at Newark, as we've seen. The minimum moonrise, 24.3 degrees this time from east, or the maximum moonrise or moonset, 38.17 degrees from east-west axis. Okay, and I give also the solstice angle here of 31.72 degrees, which I will come back to in the second part of this talk. Okay. This is a diagram from the Griffith Observatory at Los Angeles. They're doing a big thing about the lunar standstill at this particular time, a lot of different events. If you're in Los Angeles, then maybe it's worth a visit. And they give this diagram where they show 35 degrees, so being further south, of course, a lot further south than Newark in Ohio, the angle is smaller. Compared with what we just saw, 37.8? No, 38.2 or something. Can't remember. Let's go back. What was it? 38.17 degrees at Newark from the east-west axis here, 38.17 degrees. Here, 35 degrees at Los Angeles. Okay, so they show this picture where you have the solstice, the winter solstice, summer solstice angles, and the moon at its maximum position, which rises and sets further north and further south. Okay, now, like I was saying, you imagine that when you watch a moonrise, you're going to be watching the moonrise at full moon, but it's not necessarily at full moon that the major standstill takes place. In fact, it's quite probably not at full moon that it takes place. as we'll see in a second. So here you can see a moonrise over Newark. It's a time-lapse photo taken with a half moon, a crescent moon rising. And I'd like to look at that now because, as I said, it's not a point that's put forward in 1982 by Hively and Holmes. So let's look at this. So here we're behind the Newark Octagon, behind the circle, behind the observation mound. And here the moon is just below the horizon. So although we can see it on my diagram, it can't be seen in reality. And the moon is going to move on an angle. It's not going to go straight up. It would do that if we were on the equator. But because we're at a northern latitude, it's about 40 degrees latitude, just slightly over 40 degrees latitude at Newark. Well, the sun will rise at an angle of the horizon at 50 degrees. 40 plus 50 makes 90. So it's what's called the co-latitude. So it will rise at an angle of 50 degrees. And so it's moving towards the east as it rises. Okay? So according which part of the moon you are going to look at as your angle, then you won't be getting the same angle as its rising position. Okay? So as the moon rises, it's going to move towards the east. And here we see it just above the horizon. And there it is on the axis. It's on the horizon, on the axis of the octagon and the circle. And this is how we imagine this would have happened. That the people at that time would have been aiming towards this full moon, sitting on the horizon, on the axis of their monuments and banks, etc. Now, if instead of the moon sitting on the horizon, we take the center of the moon at the horizon, then this is what you would get, okay? If it's a full moon, that's what you would see. And so that's possible. It's possible. Sometimes, very often, when the full moon rises, it's not very dark, because when it's full moon, the sun is setting, okay? So it's often not very dark. And so seeing a half moon on the horizon is quite difficult. But let's say that we're in a crescent moon phase. So here, when the crescent moon is just above the horizon, well, it's giving off a lot less light, so it's more difficult to see, but it is possible to see it. However, if we were to take the center of the moon when it's a crescent moon, then that's what you would see. That's the moon as a crescent moon with its center on the horizon. In fact, you can't see it. So it seems quite obvious that if we're talking about moon observation, then what we should be looking at is not the center of the moon as the position on the horizon, which we take as the angle, but the full moon, the moon, not the full moon, but the moon itself, which is actually sitting on the horizon, okay, which is a different position. Now, I was talking about the season when this major moonrise actually happens. There's an interesting text on the Lunar Standstill Wikipedia site, which says this: the time at latitudes not too close to the equator, when the moon is at its absolutely greatest angle above the horizon over the course of the 18.6-year cycle, occurs about a week after new moon if it's in the spring, or a week before new moon if it's in the autumn. That means it will be a half moon. So Wikipedia is saying that the moment of the major standstill, the moon will not be full, but will be in a half moon position. Now, this is true now. I'm not sure if this was true thousands of years ago, but whatever. what they're saying basically is that it's very possible that the moon, when it's at its major position, is in a half moon position, which means, of course, that you have to watch it sitting on the horizon. Now, why is all this very important? I'll be coming to this in a minute, because it changes the angle that you're going to be looking at, okay, when the moon is rising. Now, if we look here at a new report which was made on the Newark Octagon in 2023, so this is last year, by Christopher S. Turner, okay, he made this new analysis using GIS, Geographic Information System, of the lunar sight lines at the Octagon and the complete listing of all associated horizon foresights. So I showed earlier the foresight at a distance, which gives a long distance angle and where the moon would come up over the horizon. And he's been working on this to make particular spots visible where he thinks building and development should be stopped because they're probably part of some ancient site and should be kept as national heritage. Okay. Now his system here is very, very precise. It uses information which gives very, very precise angles. And you can see here all the blue lines that he'd drawn maximum moon rises, and the mauve lines here are minimum moon rises, okay? So he's showing that there could be all kinds of different ways of observing, not just down the major axis, but on other lines as well. Okay. Now, his major observation point, foresight here, as I said, he gives the GPS of that particular spot, which enables you to realize that this line that he's drawn is 51.88 degrees, which is 0.05 degrees more than the 51.83 I was suggesting, and means that his observation foresight is about 2 or 3 feet away from where it will be if it was 51.83. Okay, so we can basically say we're in agreement on that angle. But again, in his table of data here, he gives the angle as 52 degrees. He gives here, if you're taking just the top of the moon or the center of the moon or the moon sitting on the horizon. These are these 3 different positions he gives. So for the center of the moon to be taken as a reference, he gives the angle of 52 degrees here. And for the moon sitting on the horizon, 52.2 degrees. Okay. Now, this may seem like a very small difference, but in fact it's very important, because all these hypotheses about the moon are being taken at a specific date, which is 250 AD. But from the angles we're seeing, if the angle of the octagon and the circle is 51.83 degrees, and that the moon sitting on the horizon is 52.2 degrees, then there's about half a degree difference between the maximum position of the moon sitting on the horizon and the angle of the monument. And it's very unlikely that people would have built an alignment to something they couldn't really ever see. Okay? So I'll be coming back to this in a second. It's a very important thing to take into account. Of course, if you're building a monument aiming at something, then you have to be able to see it. Okay? And if it's slightly off, then that's no good. It's very easy to align things. You know, if you've got a distant point, you can align things in a straight line. That's very easy. And so, anyway, I'll come back to this in a second. Now, Turner, in his new paper, also talks about this line GF here, which he says is a minimum moon angle. And here is his diagram of it. So you can see the very, very precise diagram. Now I've measured that on his diagram to be 65.34 degrees, the central axis of the mound between F and G. Hively and Horn gave a measurement of 65.63 degrees for that angle, which is, not far from the one we get here. But Turner here gives the angle of the moon, if it's sitting on the horizon, 66.4, and if it's the center of the moon, 66.1, okay, which again is at least half a degree different to the actual angle. Okay, now Hively and Horn didn't have computers to check up on their stuff. Now there are simple methods to check exactly on the altitude of moonrises and sunrises at different positions. And I'll be using this particular one to show you what the results are we get with modern day computers. This one is by Victor Reis, who I know personally, and he's been working on these questions in Ireland at Newgrange and in Scotland at Maes Howe in the Orkneys for many, many years. And he's developed this program, which is available on the internet. So I'm going to go over directly to his program. So here it is. Now I've pumped in here the astronomical date of 250 AD. I've put 40.052 as a latitude, which is the latitude of the octagon. I've given a given altitude of 0.47, which is the height which is given by Turner, Christopher S. Turner, in his recent study. The first study gave 0.51. Here he gives 0.47. I had calculated 0.50 from my own calculations. So the actual altitude slightly changes the angle. And if we look at this, and I've put major standstill here because this program enables us to calculate the angle of the major standstill with a given altitude at a given latitude for a given date. Okay, and we can also say, do we want the object, either the sun or the moon, do we want it just fully above the horizon with its center at the horizon, or just fully below the horizon? Now, just fully below the horizon, we don't want that because you would never see the moon, as we saw. Even the center at the horizon will be problematic. But that's what I've put here as an angle for the time being, center at the horizon. And the result we get here is 52.34, which from north is a greater angle than the angle that's given in these different reports. Okay, and this is for the center at the horizon. If I put sitting on the horizon, so just fully above the horizon, and I calculate, we get the result 52.61, because if instead of taking the center, we take the moon sitting on the horizon, then it will move a little further south. Now, of course, all this is very important because if the moon is further south, it's not aligned to the monument's axis. So how could that be? Now, this could be because the date they have chosen of 250 AD is too recent. Because if you go back further, then the moon is further north. But what's quite astounding here is that to get the actual angles, we have to go right back to 2900 BC. And if we go back to 2900 BC, and now we recalculate, with the center on the horizon, we see 51.83 degrees. So when the center of the full moon was on the horizon, so half of the moon was visible above the horizon, and the moon's first rays were shining straight down that central alley between the octagon and the circle at Newark, it was 2900 BC. And if we take the date for the moon actually sitting on the horizon, then we have to go back another 3,000 years to 5,900 BC to get the same result, 51.83 degrees. This shows just how important the thing we're looking at is. Okay, this slight change between are we looking at the moon sitting on the horizon or the half moon on the horizon with its center on the horizon, that changes everything. And whatever the case, the date given of 250 AD for this orientation would seem very unlikely, to say the least. So the problem with the major moon observation theory as it's propounded for the moment is that the inaccuracy of half a degree means that the incredibly precise sight line never actually pointed to the moonrise, because the moon would never have risen to the particular sight line at that date. The sight line is half a degree greater from east than the maximum position of the moon in 250 AD. Now, if their monument had been approximate, so if they hadn't really been watching for many years to get the exact angle of the declination, then the angle from east would have been slightly smaller than the perfect angle of the maximum moonrise, because they would have seen it at a lower position. They could never see it at a higher position, but they could see it at a lower position. So had their monument been approximate, then in that case, the result would have been further south, showing that they had not been able to observe precise lunar maximum. But here the angle from east is greater, so they would never have been able to observe the moon rise along the major axis of the monument. Now, is this really a feasible suggestion? It isn't, of course. If it's orientated to the moon, as everybody seems to agree, then it must be older than the dates that are given. But unfortunately, that includes putting into question the whole timeline that's been developed through carbon-14 dating and other methods, which is probably quite valid. But it does make one wonder if the people, the Hopewell community, were actually the builders of this thing, or whether they were just hanging around in it, basically. And what one must realize is that in 2900 BC, people in England were building the banks around Stonehenge. They were doing the same kind of monument, building these circular banks, which were the first things they built at Stonehenge before building the central monument that everybody knows now. Avebury, which is a massive monument, which is actually smaller than the Newark earthworks. It's actually smaller, but the banks are much higher and the ditches are much deeper. That was built in 3500 BC. Now, before carbon dating started, that date would never have been accepted. It wasn't believed at all that the megalithic builders were building at that time. Before the carbon dating, they thought it was thought to be around 1500 BC or something like that. And it does seem rather strange that people should have been building exactly the same monuments in the British Isles or in Carnac, but the ones in the British Isles are very similar to what we find in Newark, that they were building the same kind of monuments in 3500 BC, like Avebury. But although the moon is dating what's going on in Newark to that period, the archaeological results give a much more recent dating. So I definitely think it's worth looking into. Maybe I've made some terrible mistakes in my calculations here, but I'm actually using other people's data. And what is quite clear is that even in the data that's given by the researchers themselves, the axis of the monument is further from east than the maximum position of the moon that they give, which means that there's already a mistake there. It seems quite obvious that these people would not have built a sight line towards something that they would never see. Okay, so this is the end of the first part of my talk. I'll be going in the second part, I'll be going deeper, much deeper into the geometry, which has implications, again, of profoundly high knowledge in a far distant past. In the meantime, well, if you want to go and see the Newark Octagon and the circles there, then now's the moment. If you've enjoyed this video, then please subscribe to my channel by clicking on my photo below, and then you'll be sure to get news about the following installments of this talk. And the next talk will be coming out shortly. It's called Unbelievable Geometry and Measurements in the Newark Octagon. Thanks for watching. This is a moon angle, and so it's the moon that is marking out this triangle every 18.6 years. This is what's called astrogeometry. These ancient builders had somehow become aware of cosmic harmony, that they were able to express in this massive earthwork some understanding of how the universe works.